Do you want to
yeah,
turn on your camera? I mean, the other camera.
yeah. Let me share it and see how it goes. Okay, I need to kind of get better.
You're about 90 degrees. You need to rotate 90 degrees anti-clockwise.
Oh,
or clockwise, depending on which thing you're rotating.
so something like that will work.
Yeah, that's perfect. Yeah.
Let me just move the laptop away. So this gives a pretty good view, right?
Yeah, that looks great. Okay, welcome back, everybody, for Laura Reina's third and final lecture on perturbative QCD calculations. Please go ahead.
Thank you, and hi to everybody. Really enjoyed talking to you yesterday during the discussion, and then chatting on Slack after that. And I think it has been very challenging too. I mean, you have a lot of very interesting questions, I must say. So we wanted today to complete what was left out of the previous lecture. There was the part concerning the matching of the hard scattering to the initial state, to the hadronic initial state. And then we finally wanted to get to the full description of a hadronic scattering process, which is what is of most interest to us, and try to make contact this time with the reality of experimental measurements, and in particular get a feeling of really how we can estimate, and we can have a pretty good understanding of the kind of theoretical accuracy we can reach, and in particular, which kind of incredible accuracy a full control, a good control of the perturbative part of QCD interactions that are involved allow us to have, which is, after all, the goal, the goal of this discussion, just to convince ourselves and to understand why, by knowing, as a matter of fact, what seems to be a very limited part of the full dynamic of QCD, allow us, as a matter of fact, to reach pretty amazing precision and pretty amazing results at the level of real physics, the physics of colliders. So coming to our discussion, the part that we still have to sketch out today before we can get to the discussion of real processes is the part that connect in the picture that we have used many times, the hard scattering process to its origins. So to the origin that are in the proton and proton or antiprotons. So let's call them actually probably even better hadron 1 and hadron 2 that are the origins of the scattering process itself. So we have justified this part. We have justified the evolution towards the hadronization phase, so towards the formation of sprays and jets of hadrons, and we still need to justify the role in particular played by perturbative QCD in connecting the hard scattering to the initial parton densities, in particular to the initial hadrons. So here you may imagine that, as a matter of fact, till we don't go back enough to reach in the dynamic of the hadron scales that are below the threshold that we have identified as the threshold above which we can use perturbative QCD, so lambda QCD, and below which we enter a domain of QCD that we cannot describe perturbatively, everything pretty much goes the same as the evolution from the hard scattering to lower energies. So going from the hard part of the hard process to lower energies in both directions should work more or less the same way. And indeed it does, and we can use a lot of the knowledge that we already have for the emission of infrared radiation, so from the emission of both the soft and collinear radiation, identifying, however, in this process, what is different. And there is a fundamental difference that is the whole origin of the different treatment between initial state and final state, and the parametrization of initial state in a way that is slightly different from what we do in the final state. So to come to the core of the matter and to identify what the difference is, if we remind ourselves of what we have seen for the final state, so remember that in the previous lecture, we have identified the fact that universally, if we have, let's say, the emission of a gluon from a final state quark, so if we have a final state quark leg and we emit a gluon from the final state quark leg, in the soft limit, so in the soft collinear limit, these emission can be parameterized, gives us a contribution to the cross-section. So the cross-section that I will indicate in this case as if this is our sigma hard, so let's denote this by sigma h. The cross-section that we are calculating here is a sigma h plus gluon in this case. And in the soft collinear limit, the contribution, remember, goes more or less like the sigma hadronic without the gluon. And I will put some dependencies later on. And then we have the part that we calculated together, which is the part specific of the emission, which is of order alpha s. And in the notation that we have used is 2 alpha s times the color factor divided pi. And then we have the differential integration over the phase space of the gluon, which is a d omega k over omega k, where omega k is the energy of this gluon that is coming out with momentum k. And then we have an angular integration d theta over theta, where theta is the angle of emission between the initial parton that here we take to be a quark and the gluon itself. Now, if P is the momentum of the outcoming parton, so it's the momentum of the parton that is radiated, so of the emitter, we can describe this collinear kind of kinematics in terms of a variable that in terms of momentum that are parameterized by a fraction of the momentum of the emitter. And so we can say that the residual energy left after the emission of the gluon is a fraction z of the momentum of the parent. And therefore, the longitudinally, in longitudinal emission in the collinear limit, the fraction of energy carried by the gluon is 1 minus z times p. And if we do this change of variables, that is a change of variable from the energy and the angle of the emission to the z and the k perp, so the perpendicular component of the momentum, this very same expression can be written again as sigma h 2 alpha s df over pi times the dz integration variable that we have introduced over 1 minus z times dk perp over k perp. So if you do the change of variables from omega k theta to z and k perp, you will see that the expression easily comes out to be this way. And I think we have already introduced this notation in our previous lectures. In this notation, the omega k, so the energy, is nothing else than 1 minus z times p, and the k perp is indeed the product of approximately omega k. It's omega k sine of theta, so it's approximately omega k theta. And this helps you in the change of variables. Now, together with these, at the same time, we have to consider, as we discussed already, the virtual emission of the process. And the virtual emission of the process is related, let's pictorially depict this contribution like virtual gluons that are emitted and reabsorbed in the process. And in this process, the difference with respect to the kinematic that we have here is just that the momentum of the initial parton stays the momentum of the final parton. And we calculate here a sigma hard that we will call virtual. And this turns out, as we have discussed in our previous lecture, to really compensate this kind of structure. So the sigma virtual turns out to be minus sigma h, 2 alpha s cf over pi, and then the same measure of integration over the phase space. And these also we discussed is kind of the result that we derived in previous lectures, because this is all final state. And if I have to put some momentum dependence in here, so the momentum dependence that I left out is the momentum dependence of the sigma h. So the sigma h in both cases is the cross-section of the original process, so the cross-section of the end parton, from which I can build the cross-section, both the virtual part and the cross-section of the n+1 real emission. And this cross-section depends just in terms of the momentum of the parton we are focusing on, and the same would be for all the others, but for the particular momentum we're focusing on, for the particular parton we're focusing on, is a function of P. And is a function of P both in the real case, so in the case that we have above, and in the case that we have below. Now, I drew these two cases because this is what we know from the exam of and the study of the final dynamics, of the final state dynamics. And what we want to now to connect to is the dynamics of the initial state and see what the differences are. So if we now look at processes that are exactly the analogous, but from an initial state point of view, so for an initial state leg, so consider again the processes, which is a generic 2-to-n process, and this time focus on an initial leg. So this initial leg, it's a leg from which it's again a quark, because we want to do the same case, and it's also emitting a gluon. Now, if P is the momentum of the incoming object, this would be our ZP, and this would be our 1 minus ZP. Everything else stays exactly the same. We can do exactly the same calculation that we did before, and the only difference that we will see here when we have now to calculate the sigma of Higgs plus glue is the fact that the factorization, which is still in place and still has the same thing, factorizes a n-1, so an n cross-section, sigma HP, the cross-section for the process without the gluon, then now, as you see from here, is a function of ZP, it's not a function of P. So the difference here is the fact that here we have a cross-section that is a function of a sigma hard, that is a function of ZP, that factorizes the usual soft collinear factor, which is 2 alpha S CF over P dz over 1 minus Z dk per over k. And as if we now go and do the same thing for the virtual case, so if we now add the virtual correction in the same order, which is what we would do in building the parton shower, and here we do it in building the initial state, as we can clearly see, there is no such structure as a sigma hard of ZP, but there is still the very same structure of a sigma hard of P as we found in the final state. So if I have to write in this case that sigma virtual, this sigma virtual will be exactly the same that we had there. And now we see the difference between the two. And the whole point in treating the initial state different from the final state is really in this difference. And this is what brings out the structure of the initial state cross-section emission from the initial state as opposed to the emission from the final state. So the difference is really coming from the fact that now when we sum these two cross-sections, there is a total compensation of infrared structure. In particular, there is a total compensation of collinear structure between these two as well as soft. But for the other case, there is not such compensation. And this is where, as in the discussion of the final state, emerged only in the very end of the evolution, where we had somehow to regulate our lower bound of the integration of KT, and this lower bound of the integration of KT was regulated eventually just by setting the hadronization scale at the order of lambda QCD. In this case, it's even more so, and it's even more so because of the fact that when we combine these two objects, so when we combine the sigma Higgs plus gluon and the sigma, the sigma, it's just a matter of habit, the sigma hard plus gluon and the sigma hard virtual to get the order alpha S corrections of the emission, we see that the expression that we get is of the order 2 alpha S CF over pi, as we have there. There is a proportionality to the sigma hard, but this proportionality cannot be brought out anymore because one of them depends on Z. And so the way in which I can write this part is just as an integration over, so this would be, if you want, I should have called these d sigmas. So when I get to the d sigma, to the total cross-section, and I really integrate also over this object, I will get dz over 1 minus z, and the factor that now is the difference between sigma hard at zp and sigma hard at P. And this part, so these integrations that are now integration between 0 and 1 in this case, and in this case are integration between a lower bound that is 0 and an upper bound that is whatever scale q I have, is such that this part, so the part that is the difference in the mismatch between the two, is as a matter of fact finite, but the corresponding integration over kt is divergent. And the divergence is clearly the lower hand. And this is what we have to worry about. That wouldn't have happened if both the soft and collinear limit in the full matching that we see in the final state would have happened also in the initial state. So the presence of this finite mismatch is the one that makes the collinear divergence surviving. And the collinear divergence is the one that needs to be regulated somehow in the initial state. So this part, so the part that is that has indeed a final limit in the limit for z going to 1, which is the soft limit, is the part that will go in parton density terms in what we call a splitting function. This is really what will constitute the splitting function for the quark to quark gluon case, and this part will have to be regulated somehow. Now, are we here doing something again ad hoc? So is this the solution to this, as you will see, is just not to start this integration from 0. So honestly, the point, so the answer at this point is to rephrase the question and just saying, why do we have to start from 0? We know that in the regime of very low Q, we cannot use perturbative QCD anymore. We know that the farther back we go in energy to match the constituent quarks and gluons that we find in the hadron that initiated the high energy collisions, the farther back we go in energy, the more we enter the non-perturbative regime of QCD. And at some point, there is no point for us to keep pushing that momentum transfer to 0 because we are entering a regime that we cannot describe in terms of perturbative QCD. And here again, we just introduced that concept in our analytical formulation of the problem. So the solution to the problem, if you want, is as simple of saying, in this picture, in the picture that I have here, is we introduce a threshold. And we call this threshold, let's say, Q0 in terms of my evolution down here, in my integration down here. This Q0 will be what we will call the factorization scale. And I introduced the symbol that we normally use, mu sub f, just in analogy with the mu sub r, which is the renormalization scale that also introduced another important unphysical but fundamental scale in the description, the theoretical description of this process from a perturbative point of view. And the reason why it's introduced in analogy is just because these scales are unphysical to start with. So there are scales that eventually, if we were able to calculate these cross sections at all orders, would disappear from the prediction, from our final prediction, but they stay in our real and de facto prediction of this cross section because we are not able to calculate all the orders and we calculate them partially. At the same time, the analogy is also due to the fact that in the case of the initial state calculation, so in the case of the evolution from the hadron to the hadronic cross-section of vice versa, we introduce a mechanism to factor out, if you want, our ignorance and the corresponding apparent singularities that we get in our perturbative calculation in the hadron constituency itself. So this is not like, again, one more time, just swapping things under the rug. It's just that what looks here as a singularity may not well be the right thing of looking at things because we cannot push our calculation that far back to reach a zero transfer momentum. We cannot go that far low in energy and momentum because perturbative, and still pretend to do our calculation perturbatively in perturbative QCD because we cannot do that. So that's not the right regime. So it's far more honest to say that at some point we match some non-perturbative density of partons in hadrons and keep that as our unknown, if you want, or our non-perturbative densities that we have to fit from experimental measurements. And the really important point here is just that that given, we will be able to determine the parton density at all other energies up to the hard scale, the moment in which we move above the non-perturbative threshold, because that evolution is determined by QCD. And determined by QCD in a way that we can easily sketch now. And it's very similar to what we would have done in the parton shower just before, right? Just in the initial state as opposed to the final state. So how you would do that? Well, just take the same picture that we have here. So just imagine that here is again your hard part. And you are considering a parton that is coming from your hadron down here. And now given that mu for you is just now a generic scale, and eventually there will be a mu0 that you call your factorization scale or your initial scale, but this is just the running mu. So it's mu f taken to be a generic mu in between. And you just look at the differential increment of this mu plus delta mu, and you try to evaluate, and you evaluate the change in cross section sigma at mu plus delta mu with respect to sigma and mu. Of course, in this window, you will take into account both real emission, and you will also take into account in the same window virtual emission of gluons. And when you combine the two, you get the full evolution, the full form of the evolution of your parton density between mu and mu plus d mu. So let's introduce a notation before we go to this picture. So let me just go back and turn around the previous page, since I don't want to erase what I had before. And let's just rephrase these dynamic that we have introduced here. Let's put this dynamic in the context of a process like the one that I've sketched over there. So if I wanted to reparameterize things using the same kind of variables that I've used here, I would just say that, so if this is the evolution from the hadron, and this is the scale Q0 or mu f from which I'm starting from, and this is the emission of the gluon that, so with momentum k, that we have considered over here, the parton that is coming out from the hadron. So the difference that I want to make with respect to the drawing that we have here is just that this P now has to be connected to the momentum of the hadron. So if I wanted to connect here to the momentum of the hadron, this parton, which is P, this parton will come out with some fraction x of that momentum. And at this point, the collinear splitting will be the same as before, but in terms of xp. So this parton will have a fraction of momentum z of xp, and this parton will have a fraction of momentum 1 minus z of the xp. Now, this very same picture can now be rescaled if I want xp to be the final fraction of my momentum. So I want to rescale now this picture to build it into that one just by the fraction x. So I want now the picture to look like this. This is again as before. And now I want this fraction, the final fraction of momentum that is getting into the hard cross section to be xp. So I will rescale these to be xp, and I will then rescale everything dividing by z. So this fraction momentum will be x over zp. This fraction of momentum then will be 1 minus z divided z times xp. So xp will be the fractional momentum of the parton density that is entering in the hard cross section. So if I write my cross section at this level, the level of the cross section before the rescaling will be simply given by something. So I can write the cross section for this process from just one emission as I have there, using what I have, what we have derived both in terms of soft collinear factors and in terms of the sum of both the real and the virtual contributions. So I can rewrite that in terms of a cross section that now looks like 2 alpha s CF over pi. And then I would have the integration between Q0 and Q in dk perp over k perp. And then I would have the integration this time over dx and dz over 1 minus z. of the difference that we saw before. So this term that we have here, that was our sigma age at zxp minus sigma age at xp. This time times the density, that is the density of finding at this level the species that I'm looking at, that in this case are quark, with the fraction x of the parent part momentum at a scale that is our Q0, right? So if I now switch to the new rescaling and I look at the difference, I look at the density that I can get at mu plus delta mu. So I calculate the cross section at mu plus delta mu in terms of a density Q at mu plus delta mu. And I calculate the cross section at a scale mu in terms of a density Q mu. I can get a differential equation that gives me the evolution. So, and the differential equation that I get is the one that you're probably quite used to, which is tells you that the dq at x and mu, the derivative of q with respect to the logarithm of mu, and what is most common is just to phrase these in terms of mu square, is alpha over 2 pi times the integral. Here we have taken the derivative with respect to a scale. So in these terms, the integration over dkt goes away because it's a differential in that. And I would have the remaining dz over z at x, starting from x to the upper bound of what I would call now the, what I called in our previous discussion, the splitting function, so of a quark going to a quark, which is this factor over here, to which I now associate a symbol, which is the PQQ of Z, and then the density at a scale that originally I called X in here, but because I've rescaled everything by Z, it will be at the scale X over Z. And I put this mu. So this is the equation that in this very simple case, considering just one species of partons that are quarks in this case, and the splitting of a quark into a quark plus a gluon, gives me the evolution of the densities of quarks at a generic scale mu with the scale mu. So this scale mu will be my factorization scale, which is the scale at which I separate the non-perturbative from the perturbative. And the evolution with that scale is just governed in terms of the splitting function that I can calculate perturbatively, order by order in alpha s, and an original, if you want, the density at the scale infinitesimally close to the scale in which I'm calculating now the pattern, the new density, and that eventually will connect any density to the scale in which I measure the original pattern density. So this can be, of course, repeated for all the different patterns that I have in a hadron. So I can play exactly the same game for splittings of a quark, for splitting into of a gluon into a gluon plus another gluon. I can play the same game for a splitting of a quark, of a gluon into a quark and an anti-quark, and I can build at this point a matrix of equations because each single species will receive contributions from density at a lower scale that can be both quarks and gluons. So the generalization of this very simplistic equation gives you the full set of what we call the evolutions equation for parton densities that are the DG lab equation, originally Altarelli-Parisi equations, and then complemented by DGNL that was developed at the same time and with the same formalism, just to give us a set of equations that very importantly allow us to calculate the pattern density that enter the pattern density that enter the hard cross section in terms of density that we can measure at a lower scale, at any scale, as a matter of fact, and from which they are evolved, knowing, without knowing from first principles, the original non-perturbative core. So when we think of PDFs, so when we think of pattern distribution functions, so we distinguish really in our mind two separate components. One component is a non-perturbative component, and is the non-perturbative core that can be fitted from experimental data. But how? We fit them from experimental data by measuring observables that are measured at energies. and in kinematic regimes where perturbative QCD is valid. So those observable, those hadronic observable that are the ones that are related to scattering process at this scale are measured using the full-fledged apparatus are calculated and measured and compared to calculations that are obtained using the full-fledged apparatus of perturbative QCD and the accuracy that we can get from perturbative QCD, including the evolution of the density that entered the scattering at this scale from density that we don't know, but that we can fit from data because we can predict consistently and accurately their evolution from the low scale to the scattering scale. And this is precisely the game and the framework that is set in place in all the different PDF fits that you normally use in the prediction for hadronic cross sections. So
there's a question in the chat.
Sure.
Oh, do you want me to read it?
Oh, sorry. Yeah. Sorry.
Sorry. Yeah. So the question is PQQ the splitting function defined before? And also, is the equation the sum of two diagrams or just one diagram?
The PQQ is the splitting function defined before. Yes.
Okay.
Of course, here we are not being careful about the exact factors in there. I may be missing. So, for instance, the color factor, I have included it into the PQQ. So the PQQ has a structure if that is the one you're used to. So if I have to write in terms of z, it would be a 1 over plus z squared divided 1 minus z plus distribution. This plus distribution is just the one that comes out of this structure. Sorry, can you see mine? Because somehow I don't see it anymore. Okay, sorry.
Yeah.
The analytic form of the PQQ, apart from the colors factor, is the one that I just wrote here on the paper, and is in terms of a plus distribution. So you are probably familiar with this plus distribution, but what the plus distribution is just a distribution that you define by integrating, let's say, if I have a function of z, and I integrate any function that has a smooth behavior with z, the plus distribution is defined as the integral over dz of g of z, which is singular form, but multiplied by f of z minus f of 1. So I basically subtract the singularity of g of z by the smooth behavior of the function that the distribution is integrated over. So this is the meaning of this plus distribution. So the PQQ is indeed the splitting function. And the reason why it has this form, so it comes in the form of a plus distribution, is because, as we showed before, it is obtained by a difference of objects that have a z dependence and is equal to 1 fixed dependence. So it's the difference between two functions that are really these two functions that are evaluated at z and at z equal 1. The second part of the question was, can you repeat it to me? If they include both diagrams?
Sure. Yeah, if it's both diagrams.
Both the real and the deformation, yes. So, is there any other question? Okay, so to conclude the discussion on initial state, the effect of perturbative QCD in the initial state. The initial state eventually will have to match to a non-perturbative domain. And the non-perturbative domain is the hadron that comes, or the hadrons that come into the collision. Now, how do we match to that non-perturbative domain? By evolution. The evolution is the evolution of a non-perturbative core of parton densities that we don't know. And we cannot know in terms of perturbative QCD, and therefore we just give them a name. We just call them the bare perturbative, non-perturbative cores of our PDFs. But what we can calculate is the evolution of those objects from the non-perturbative scale, or from the scale at which we first start applying perturbative QCD, to the hard scale. Now, this is exactly the same principle. You may still be wondering how well defined is this process to start with. And what are we doing when we take those densities from a generic set of PDF that can be an MPDF or CTEC or TTW or anything else, right? So the principle on the basis that sets are built is exactly the same. It's exactly again the principle that you can fit the non-perturbative course because you know the perturbative evolution. And when they the game that this set plays, to provide you with the objects that at a scale of your hard process you need in order to calculate the hard process, is to implement this exact evolution mechanism and fit the non-perturbative course from a set of data that has been growing enormously with time, and for which I wanted just to see if I can show you a recent determination or what goes into one of these fits, for instance. So here is taken from a CTEC paper, the most recent one that has produced the CT18 PDF set. And I'm afraid that probably this doesn't come out that clearly, but what you see in here is in a plot so the PDFs as the pattern distribution function, as we have seen here, they are function of x and they're function of mu, right, of the scale. So here is in a function of x, in the what we were looking at before, they're function of x and they're function of the scale. So here, as a function of x and as a function of the scale, they tell you each single little one of these points. Notice that x and q, they're linked together by the central mass energy of a given process. So that's the reason why there is this pattern on the picture, because there is a relation among them. Now, in this plot, what they're telling you is for each single little dot on this plot is a measurement. So it's a measurement from a specific experiment that is quoted here on the side. And if you look closely at all these experiments, they're spread out over many, many years. They're spread out over decades. There are experiments that goes as back as the 90s, right, or the 80s. And so they come from experiment pre-Tevatron for EP experiment, then from Tevatron experiment, PP bar experiment. And the interesting thing that they may start seeing here is just that there are more and more entries coming from the LHC. What this means is just that the way these sets are built is just by using pattern distribution functions in the calculations of physical observables that are measured at colliders, and comparing the experimental measurement with theoretical predictions that use those pattern distribution functions at the scales at which the process happens, by evolving them using perturbative QCD, using the DGLAP equation from some non-perturbative core. Comparing these predictions to experiment, you can extract the non-perturbative cores. And the more, and those are the ones that are with different mechanisms, and the non-perturbative cores that are extracted can then be used to give you PDF fits at all scales for all processes that you want, and not only the ones that have been used for the fit. So for your fit, you pick the most reliable, the better predicted, the most meaningful. There are many different components that enter in the choice of processes that are used for PDF fit as input to the PDF fits. Once those processes are used as inputs, they will determine the non-perturbative core using a fully perturbative framework, both for the evolution and for the calculation of the rest of the cross sections that enter in these processes. Once that is done, you can now provide PDFs, pattern distribution functions, pattern density at any other scale and for any other process because they're universal. What we have done in this discussion is not related to any particular process. And the pictures on the bottom is just for your illustration, is just the illustrations from the same papers, what the behavior of these pattern densities look like at different scale. Here at the low scale, very close to the non-perturbative regime. Here at the high scale, that is much closer to the scales at which the hard collisions in our bubble actually happen. So this somehow should give you a little bit of the idea of what enters the part of the evolution that we had not discussed yet, which was, so in particular, what is the role of QCD in that part of the evolution? Is there any other question at this point? Because I would like to transition now to the putting together all the elements of our discussion, both of these last one and
there's a question. Is there no chance to get information on the PDF for Q close to lambda QCD, Q less than 1 GeV? I think you just can't do deep. You can't do deep inelastic scattering there.
Maybe I can look at the question. So is there no question of getting information on PDFs close to the lambda QCD scale? Is that the question?
Yeah.
Well, no.
I think the Q evolution you do by running, right?
Sorry.
The Q evolution is calculable,
it's
right?
Calculable,
Except when alpha S blows up, then it becomes
that's a point
inaccurate.
Yes, that was a message. I hope that was clear, right? So that the evolution is what you calculate perturbatively.
Did that answer the question?
Now, the question probably is more related to, I don't know if that is your doubt, but the doubt is just if there is a more fundamental way of calculating pattern distribution functions, getting really to calculate them at the scale in which QCD is not perturbative. I don't know if this is the question, but again, here we go back to things that are not in the realm of perturbative QCD, so to a sort of approximation of the exact solution of QCD, or the numerical approximation of the solution of QCD. And there are, of course, other investigations that you can do. For instance, a very new, recent, I would say, not a new idea, but a recent development in PDFs is the study of PDFs in lattice QCD. And this will be a determination that clearly is more related to a first principle determination, that not what we do here, where we do not determine them at all. So as Heather was pointing out, what we do in perturbative QCD is just, and what is normally done is just taking care of the evolution. And relying, just lumping and pushing, collecting our ignorance of the non-perturbative part of the story into this non-perturbative course, that then, thanks to the precision that we can reach on the perturbative part, we can very precisely fit from data. And actually, to give you the idea, I had a plot that I didn't show because I thought that probably was time to move on, but given the question, I may wanted to show this to you. This is these are plots that I owe to one of the leaders of perturbative QCD, Gavin Salam, and that shows you 4 different kind of processes. Processes that are gluon-gluon initiated, or quark-gluon initiated, or quark-quark initiated, or quark-anti-quark initiated, which kind in a parameterization in terms of mass and rapidity, right, for for a given hadron-hadron collision, for a given PP collision in this case, because it's done at 13 TeV, so is very much LHC oriented. And indeed, the set of PDF that has been used for this study is a set of PDFs, the very global set of PDF that has been developed specifically for LHC, taking into account PDF uncertainties that are coming from comparing different sets of PDFs. Different set of PDFs differ by the fitting algorithm and by the inputs that they consider. With all the inputs being the same, they still differ one from the other for the fitting algorithm. And some of the algorithms may be very different from others. The results are equally different. To minimize or being, in a way, to minimize the kind of arbitrariness we have in using one set with respect to the other, we can work out a sort of common framework or envelope of all them. And this is what this PDF for LHC set has achieved. And in this plot, what you see is the kind of uncertainty on pattern luminosities that are these gluon-gluon, quark-quark, quark-gluon, and quark-anti-quark luminosities that you expect from PDFs. And as you see, in most of the phase space, you never reach more than 10%. It's only on extreme regions of phase space of the PP collision that you reach more than 10%. So as a matter of fact, this approach that we are having is not so approximate. So the fact of knowing very precisely both the hardcore and the evolution from the perturbative domain of QCD to the non-perturbative domain in which this pattern density, the non-perturbative cores really live, put us in the condition of having allows us to have a theoretical uncertainty that is very much under control. It is very little. This doesn't mean that a more accurate and first principle study of PDF would not be useful. Actually, it would be extremely interesting, extremely important. But it's just to give you the idea of where we stand right now and which kind of impact the knowledge of PDF and the knowledge of the non-perturbative part of the game plays, and how much does it affect our prediction. Not much, as a matter of fact, at the moment, and very much systematically under control. So improvable because you can improve the perturbative evolution. It's probably used to be a very important part of the uncertainty. In a lot of cases, it is not anymore the leading part of the uncertainty. It's just one of the less relevant, not less relevant, but less worrisome part of the uncertainty at this point. Okay, so if there are no other questions on this topic, I would like to put all the pieces of the game together. And so, as in the description of a hard collision that we had, so in the description, we go back to our picture of a hard collision in which we justified the use of perturbative QCD in the evolution back to a hadron here. And we have justified the use of perturbative QCD in the evolution in the Parton shower regime to the hadronization phase. And of course, we have justified the use of perturbative QCD in the calculation of the hard part. Now, the fundamental question that we wanted to address today is how far, so how do we push the precision of perturbative QCD, and why? So why do we want to push that precision, right? And how do we achieve it? Now, this is where very much we need to enter in direct contact with what we measure and understand what we measure in terms of the structure that we use in order to describe those processes that we have discussed. And now we are going to look at it even more in detail. Now, just to write to make contact with what we are going to discuss more specifically, the process that we have been discussing so far has a hadronic cross-section in terms of the collision of the two hadrons. That is, I wanted to write as in general to a generic final state that, as we know, can be either inclusive or exclusive. That we now know we can translate into a formula what we have discussed in words before, will be done by a convolution over two fractions 1 and 2 from the hadron 1, parton from the hadron 1 and parton from the other hadron 2 of the density of a given parton, let's call I, from hadron 1 with the fraction x1, and at a given scale that we call the factorization scale from the first hadron, and the density of a parton j from a hadron h2 that is coming with the fraction x2 from the second hadron at the same factorization scale, summing all the possibility of sub-processes I and j that we can have for a given global process that is initiated by hadron H1 and hadron H2, times the hard cross-section as the parton level, which is the one that lives here, and we indicate as Sij for parton I and parton j to go into the final state x. And this cross-section will also depend on x1 and x2. It will depend on the overall hard scale of the process. It will depend in the case of pure QCD on alpha S and nothing else. And it will depend on the factorization and renormalization scales that has been introduced into the game so far at two different levels, at the level of the pure hard cross-section or at the level of the factorization of PDFs in the initial state. Now, In the inclusive case, this is the end of the story. In the exclusive case, this can be multiplied by, it could be further convoluted by a function that I don't specify here, but is a function that can select a specific final state. And here I'm talking about function that can select particular kinematics, they can select particular jet structures, they can select a particular final state exclusive properties that we don't want to deal with at this point. What we are mainly interested in is just to assess where is and where do we expect the precision of our theoretical prediction to really reside and to really matter the most. Now, if our approach is the one that we have described so far, it is really crucial because perturbative QCD rules both the evolution of the initial state and of the final state towards the initial state and final state, the non-perturbative regime of our process, to push the role played by the hard cross-section as far as possible into the matching of these evolutions. And the reason for that is just that as we have discussed already, or as we have mentioned several times already, and probably it's now the time to emphasize it even more, the accuracy of the theoretical predictions and the accuracy with which perturbative QCD can really predict and fully, with really high accuracy describe a given hadronic process is set very much in the initial hard scattering process. We have seen that the rest of the dynamics is quite well modeled by the infrared properties of QCD, but if a process happens with a certain hard kinematics, the more accurately we describe that hard kinematics, the better our prediction will be. And the structure of the process itself will evolve mainly based on infrared radiation and collinear radiation, but is set really in the initial stages of the hard dynamics. So the more accurately we are able to predict the hard part of the story, the more accurate our global prediction will be. So the prediction of these sigma hard is really crucial. So the prediction of what we will call sigma hard here at the particle level is really crucial to the whole success of the enterprise, to the success of the story. And at the same time, the whole success, the success of this big enterprise is also related to how carefully and how precisely we will match this sigma hard to the pattern shower and to the PDF. So when we push the order of the hard cross-section, there has to be a parallel effort to also push at the same order in perturbative QCD, the matching to both the pattern shower evolution and the PDF evolution in such a way that the boundaries of the non-perturbative regimes are reached with a full-fledged NLO or NNLO or even higher order perturbative QCD evolution, keeping as much information about the hard process as possible. So in playing this game, therefore we can sort of picture, if you want, the calculation of sigma hard as affected, so pushing the order in which we calculate sigma hard, or how to improve the precision in the calculation of sigma hards in several directions, I would say. But there are some most important ones and some main ones. So one direction in which we can definitely improve in the accuracy of sigma hard is in pushing the perturbative order. Now, the other direction in which pushing the perturbative order by order, so what we call in a fixed order fashion, can be not sufficient is if in our particular process, in the process that we are considering, some particular classes of corrections are very important. You remember the discussions that we had in the previous two lectures that in processes that involve very large differences, very different mass scales, or in processes that are very exclusive, so in which we have introduced some artificial thresholds that are due to cuts that we impose on our process or to artificial selections that we make. Artificial not because they're not physically meaningful, they may be dictated by the experiments, but they're artificial from a theoretical point of view. So from the point of view of calculating our fully inclusive integration over the phase space of the process, we may introduce in the calculation corrections that logarithmically depend from the ratio of these scales or from the ratio of, for instance, the transverse momentum cuts that we impose on our process. And therefore, as we discussed previously, the perturbative expansion in alpha S may result not to be accurate anymore, and we needed to identify in the behavior of the cross-section particular classes of corrections that are proportional to alpha S, but also to powers of this logarithm that are brought into the discussion by the structure of the theory. In that case, you enter the very very well developed and also very technical, if you want, domain of resummations. And so resummation of large corrections at all orders becomes very important. And this is something that we will not particularly have the time to discuss, given the finite amount of time that we have in understanding processes of this complexity, but that I wanted to, I've mentioned to you several times because this is something that you may encounter and that you have to take into account, and also that you will see in some of the examples that I hope I have the time to illustrate it to you. So pushing the perturbative order is what we wanted to justify a little bit more today. And why do you want to push the perturbative order? Well, the first reason why to push the perturbative order is just to lower the dependence on the unphysical scales that are present in your cross section, and they are the factorization scale and the renormalization scale. So why do you lower the dependence on these scales when you go to higher orders? Well, this is probably we have already even mentioned this when we looked at the running of alpha, but somehow is very intrinsic to the structure of the theory itself. So a very simple example can be worked out if you, so let us first write this here. So we say, why do we push the perturbative order? To lower the dependence on mu r and mu f. And why is that? I want to keep this paper for later, but just to quickly illustrate why we do that. Well, if you take a simple E plus E minus process, so E plus E minus into x, and I wanted to take this process because the only dependence on a scale here is the renormalization scale dependence. There is no factorization scale dependence. If you then go to a process that is pp to x, the same, you will have both mu r and mu f, but the same phenomenon that we are now going to very briefly illustrate will happen for mu f as well as it happens for mu r, and it's all based on the fact that the overall cross-section does not have to depend on this unphysical scale if you were able to calculate all the orders. So if you calculate the cross-section for this process at next to leading order, it would depend on the normalization scale because you calculate only one order. And the general structure for any plus E minus process is just that it starts from a given sigma 0 that does not depend on alpha s. And then it adds to these with some coefficient that I can call C1, some dependence at order alpha s, some dependence on mu r that is brought in entirely by the fact that at the first order of QCD correction, you pick up corrections of order alpha s, and alpha s depends on the scale. So this is the structure of your cross section. Now, you know, if you wanted now to calculate your cross section, if you now wanted to estimate the dependence on this scale, you want to calculate the cross section at a different scale. So if you calculate the cross section at a different scale, given that the only dependence on the scale that you have is in the coupling, is as to say, how does alpha s depend on the scale? Well, we know how alpha s depends on the scale. We know that alpha s of mu r is equal to, at the first order, alpha s of q, let me write it this way, is alpha s of q divided, as we derived the first day, 1 plus alpha s at the scale q, the first coefficient of the beta function, and a logarithm of mu r squared over q squared. And let me write here plus higher order, meaning that we have calculated alpha s from the beta function at first order. So it's, here I call it an NLO. And it's an NLO because it's an NLO of any plus or minus process. So it's the first order of QCD corrections. And therefore, I'm fine just by looking at the first order in the beta function. In a process that starts at order alpha s in a PP collision, I would have to push the order even higher. But for any plus or minus process, this is totally fine. Now, if you expand, if alpha s is a small parameter, and you expand this alpha s of q, remember we did this even the first day, this will be something like the first order in alpha s, it will be alpha s of q times 1 minus alpha s b0, the log of mu r square over q square, plus higher orders. So plus order alpha s square. This is what comes out. And so if I now re-express this process in terms of the new scale, this process will now be written, the theoretical expression that I have will now be 1 plus, sorry, C1 times alpha s of q, and then I have a minus 2 minus 1, sorry, not minus 2. So minus what I have over here is minus alpha s of q square times b0 times the log of mu r square over q square plus higher orders. That now becomes at this point alpha s q. And this calculation I've done just to show you that if you do a calculation in this case, including the first order of QCD correction for any plus or minus quantity, the change of scale from mu r to another scale q brings in an ambiguity that is higher order. So you see that the ambiguity proportional to mu r comes here, and it comes in at higher order with respect to our calculation. So this is why we say that the scale dependence of a given process in QCD is typically an indication. So if you study the scale dependence of a process in QCD, the dependence on mu r that is naturally present in your calculation for any plus or minus or for a PP process, for a generic process, you have this dependence should be higher order. And you see it here, and it gives you a first feeling of how your prediction of that particular observables, of the theoretical uncertainty that you have on the prediction of that particular observable. Now, when you go on PP, the same is true for both mu r and mu f. And the overall statement and the result depends fundamentally on the fact that if you are able to calculate this cross-section at all order, this cross-section at all order will not have to depend on the scale. So it is natural, and you see it just in these, it's not implausible, actually, very reasonable to see that at a given order, when you do your calculation at a given order, your cross-section, the dependence on the scale is pushed to the next order, which is precisely the order that you're missing. And if you had to include all the orders, this dependence will go away. So because of that, this is coming back to our previous picture, so to our previous diagram. In order to improve the theoretical accuracy on sigma hard, we want to push the perturbative order. Why we want to push the perturbative order? To lower the dependence on mu r and mu f. And we have seen why, right? Because this is the first reason why. Now, another reason why you want to push the perturbative order, and this is a little bit more subtle, less obvious, let's say, as with respect to the one that we discussed so far, or if you want, is less rooted so obviously into the structure of the theory, because it just depends on the form of the running of the parameters of the theory and how they are naturally expressed in a perturbative theory. The other reason why you wanted to push the perturbative order is just to add to better describe the process that you are considering in terms of the actual multiplicity that is involved in the process itself. What I mean by that is just, so I would probably speak here of to improve the multiplicity of final states, and at the same time to include all possible initial states. What does it mean? So the first statement is related to the fact that if you have a process, for instance, let's just be very brief in explaining this concept. If you have a process that, for instance, involves 3 jets in the final state, you want to have at least 3 partons in the final state. So sometimes something like that does not come into your game till higher order, depending on the process that you are considering. How this means, what does it mean to include all possible initial state? It means that certain processes do not include all possible partonic initial states if I don't go to higher order in QCD. And let's take an example that is a sort of canonical example from this point of view. So take a process that starts as a 2-to-1, like a Drell-Yan process. So a Drell-Yan process that we will use in one of our illustration in the following is a process for which proton-proton just produce a vector boson. So either a Z or a W or a photon. And then they decay leptonically or hadronically, typically leptonic. Drell-Yan is a fundamental process in collider physics. Now, if I calculate this process at the lowest order, this process is just made of a QQ bar, let's say, going into a Z. Let's just start with one specific channel. But if I go to higher order, and so the process is just, let's draw it in the piece of paper that I have here. The process is just a QQ bar into Z, and I have a process like this one. Right? But if I now start including order alpha S corrections, all of a sudden I can have a process that is also a Q glue going. I clearly have a process that is a QQ bar to Z plus gluon, that is just a gluon radiated from the previous process, with the gluon radiated here or radiated there. But I also have this process here. So I have a process in which the initial state is a gluon, and the final state is a Z plus Q. So I started with a channel that was just a QQ bar, and I'm ending now with a channel that is both a QQ bar and a Q glue. So I have both sub-processes contributing to the total cross-section for the production of a Z from PP or PP bar. Now, does this make a difference? Yes, it can make a big difference. And the reason is all related to the initial state parton densities. So depending on the energy at which you are, the parton density of the new partons, of the new subchannels, so the parton luminosity, as we called it in that colorful plot that illustrated for us the different uncertainties, at the next order also include a Q glue. And if the glue density is large, this channel may even be dominating with respect to the other one, or may bring in a sort of uncertainty that is different from the one that the previous one had. So a lowest order calculation is totally unreliable at this point. And the only way to obtain a reliable theoretical prediction is to add another order, just because it completes the process. So this is more or less the general structure of what we have. So the question of how do we assess, if you want, the theoretical uncertainty of a process, and why the theoretical uncertainty of a process is improved by going to higher order in the perturbative expansion. So in higher order in the calculation of the process within perturbative QCD, it's just because we improve both on the stability or on the dependence of this cross-section from the unphysical scale that a fixed order calculation brings into the picture, so randomization and factorization scales. And at the same time, we have a better insight into the structure of the process itself. And this, as we already commented in a previous lesson, does not go forever. Meaning that by the time you include, depending on the process, the first 2 or 3 orders of perturbative QCD calculations, you have pretty much included all the possible characteristics, hard characteristics of that process, of all the possible features of the hard process, both in terms of subchannels and in terms of kinematic peculiarities that process may have. A process may start as a 2-to-1 process and all of a sudden become a 2-to-2 or a 2-to-3 process because of QCD corrections. Well, the kinematics may have a big role. A process may start with a specific, very limited color structure, and all of a sudden, as we have seen, include QCD correction. That's a big change. If you don't go to the next order, to the first 1 or 2 orders in perturbative QCD, you don't see that. But by the time you have done that, it doesn't probably pay to go to the 5th order, because the same kind of characteristics will be there over and over, and you have somehow filled the big steps. So this brings us to the towards the end of our lectures. I'm going to use probably 5 or 10 minutes more with respect to I guess 3:15, which is when you are supposed to end, to lead you through a few examples. And before we look at the examples, let me, or maybe we can comment on the examples directly. So let me get some plots that I wanted to show you to illustrate this point. I wanted to show you this very busy plot that I don't know if you can see quite well, but it will be in your notes. So let me illustrate for you what this means, what you, see if I can just point to that even better. So what this plot show is a plot from Atlas and from the Atlas collaboration that compare experimental measurements for some 2-to-1 for the LHC, so 2-to-1, 2-to-2, 2-to-3, 2-to-4 processes that are of particular relevance to colliders. It compares the LHC measurements that are here illustrated in different colors depending on which phase of the LHC they refer to, so the initial 5 TeV, and then the 7 TeV, and then the 8 TeV, and the 13 TeV, with theoretical predictions. And here you can see how theoretical predictions, including their uncertainty, which is the width of the gray band, compare to experimental measurements. So the band of the experimental measurement is, of course, the experimental uncertainty. Well, there are, of course, cases when you go to large multiplicity in which a theory fares relatively well. So the theoretical predictions at the moment are very much are better than experimental measurements for the moment. But when we go to 2-to-1 processes, you can see how precisely these 2-to-1 processes, like the Trillium production or the production of Higgs that is illustrated, I don't see it here, but is the Trillium productions in particular are so precisely measured experimentally. You can see how 2-to-2 processes like TT-bar production, which is fundamental to collider, is precisely measured. Even some of the vector boson, double vector boson productions, electroweak vector boson production are quite precisely measured experimentally. And for some of them, the theoretical precision is barely comparable, if not larger at the moment than the experimental precision. And for several of the 2-to-3 processes that at the moment still have a large experimental uncertainty, not all of them, some of them, because if we look at TTZ or TT gamma, they're not that bad at the moment. Well, you have to take into account that the LHC is still analyzing a wealth of data. The LHC is moving on to a high luminosity LHC phase that will have 20 times the luminosity of the LHC now. So we are moving from what is called here the femtobars era to the attobar era, in which we will have so much statistics available and so much luminosity available that clearly and so much more experience also in experimental selections and in experimental measurement, that clearly a lot of these experimental errors will shrink. And probably, most likely, even for 2-to-3 processes that are extremely important, both to test the standard model, because these are processes that encode tops and Ws, processes that are backgrounds to a lot of new physics measurements, we will need to shrink the theoretical errors quite a bit in order to compare with them. So we will be in the same situation in which now we are for some of the 2-to-1 or some of the 2-to-2 process, in which the theoretical error is probably not as good as the experimental error, in spite of the fact that a lot of these gray areas that you have seen here, they already take into account quite precise theoretical predictions that include at least the NLO level of QCD prediction, if not the N square LO, if not the N cube LO of theoretical predictions. So this is quite amazing. And this comparison with data is indeed what has driven, if you want, the theoretical community working in precision QCD in the last 20 years. You have probably heard that in the last 20 years or so, because people like to use this term, the community has undergone what we call the NLO revolution, right? We haven't said much about this here because the NLO revolution is nothing else than the fact that for all or most of the standard model processes that you can think of. So the standard model process, for sure, all the standard model processes that you see in this table that are up to 2 to 4 in the final stage, so the 2 to 4 multiplicity, but for much higher multiplicity as well, all standard model processes are now calculable, including the NLO order of QCD correction. So that is a given, and these have been automatized. You can, of course, you still need a lot of wisdom in order to interpret what is coming out, but from the calculational point of view, that is not a problem anymore. Has been addressed and solved successfully and provided to the experiment. What we are living through now is the exploration of the NNLO in perturbative QCD. And this has been active for the past several years, at least definitely very intensively in the last 6 or 7 years, or probably in the last decade or so. And of course, it has started with processes that are 2-to-1. It has now accomplished incredible results with processes that are 2-to-2, like I was saying, the TT bar. So here I refer to Trillium Production, to Higgs Production in the gluon-gluon fusion, to Higgs Production. Here I refer to TT bar production, double vector boson production, and Dij production, and so on and so forth. And we're now attacking or thinking of the 2-to-3 production. This has been an extremely fruitful field. It's fruitful from the point of view and fascinating from the point of view that it has introduced and it has explored areas of theoretical developments that are very different from the NLO. To attack a problem like this one, in spite of the fact that it's just 1 order more, from the analytical point of view, from the numerical point of view, a lot of new domain had to be explored, a lot of new ideas have to be introduced to the boundaries of bringing into the game completely new mathematical structures that don't resemble anymore what was normally used in an NLO calculation, but will have an impact on that, and will have an impact on the full structure of QFT in general. So it has brought us to rethink many times how we interpret amplitudes, scattering amplitudes, how we interpret their roles in a generic QFT. Has been a field that, of course, would deserve a long series of lectures by itself because it is extremely different from what we have experienced so far in perturbative QCD, and extremely fascinating. What we wanted to see here is the reason for that. So why do we have to go up to this point? We saw it in this very global plot. I wanted to illustrate it to you with a few, just a couple of more examples. So the first example that I wanted to show you is the most fundamental one, if you want. This is a Trillium Production, again, as I was saying. So here it is illustrated. So the processes that are considering are the one that you see here, right? And here is a theoretical prediction of a few years ago, as a matter of fact. This was one of the first calculations that was pushed to NNLO, as you see in this plot. And here is a recent experimental measurement. And the reason why I show you this recent experimental measurement is just to look at the magnitude of the uncertainty that they have on the experimental measurement. So this is Z production explored in different channels, E with the Z decaying into electrons, with the E decaying into muons combined. And it gives you the statistical uncertainty and the total uncertainty. And here is the kind of results that they have with the experimental uncertainty included, that is then blown up and better illustrated in the lower plot. And if you look at the scale here of their uncertainty on the value that is then given point by point in this distribution of each single bin in the PT distribution of the leptons that are coming out from the decay of the Z, is the percent level. So if you look at how much is this band, in most of the PT of the lepton region that is explored by this distribution is at the level of 1%. So this is really tiny. It's a really precise measure, which is great, because these distributions are, Rayleigh Young is a sort of standard candle for collider physics. Knowing this distribution so well, and this tells you how much we are able to predict it just on the basis of pure perturbative QCD, right, in a hadron collider. That is what we have here. If we could have a theoretical prediction on the side that is equally precise, we could use these as a measurement, for instance, of pattern luminosity. This is the typical process that can be used as an input to PDF fits in order to derive the PDF unknowns that are the non-perturbative cores. But we need this level of precision in order to do that. And why do we need it? Well, you can see it in the plot on the right. So here it illustrates the calculation that goes into the comparison with this data. Here it illustrated in terms of the double differential distribution of the cross-section as a function of the mass and the rapidity. Now, the mass is the mass of the produced object, and you can imagine that this is related to the mass of the lectins that are coming out. So it's very much related. It's not exactly the same thing, but it's very much related to this kind of distribution. So what I wanted to illustrate to you here is the effect of going from leading order to next to leading order to next to next to leading order. So when you look at the LO and so the bands here are obtained by varying the factorization and the normalization scale. Now, they're varied, as you see here, by a factor of 2. This is totally conventional, but it's just to give you the idea. They could have varied it by a factor of 4, but it's just here to give you the striking image of the fact that if you vary the factorization scale by an arbitrary factor of 2 around some central value that is here naturally chosen to be the mass of the Z, because this is the scale of the process. At leading order, you have a huge uncertainty. And this huge uncertainty is just due mostly to dependence on the factorization scale that is not compensated by anything at this order. But when you go to the next leading order, so when you include the first order of correction, just the first order of QCD correction, look how the band by itself shrinks. Now, it also points to a different problem, the problem that the two bands do not overlap at all. And when you see something like this, it's a clear indication of the fact that the perturbative expansion has not stabilized yet, has not quote unquote converged, if you want, to that asymptotic value that then will be stable for a long way, much longer than what we need in order to compare to experimental data, and for which you have reached the sort of plateau that you're looking for in your perturbative QCD prediction. So when you see something like this, is also a signal of the fact that you have to keep going. And indeed, you see that when you add the next order, which is the red line almost that you see here, indeed is a band that is obtained again by varying the normalization factorization scale. What you see here is just that the band is totally included within the previous NLO band. So it's converging scale dependence wise. And the dependence on the scale is minimal, is negligible at this point. Now, if you had to plot on this very same calculation, the result of an experiment, you would be able and the corresponding results obtained using, so if you had to reproduce this exact plot, using different kinds of pattern distribution functions, you would obtain slightly different bands. And if you then had to superimpose to these, let's say, experimental results, you would be able basically to tell pattern luminosity from pattern luminosity. So this is an amazing result. It's an amazing example that really shows you where precision matters and where precision goes. So it's able, just because that is what, that kind of information will then affect all kind of other hadronic observables that you may decide to calculate or you may decide to measure, including measurements in physics. So this is something that has a repercussion on everything else that you may want to derive from your collider physics experiment. The next example that I will quickly show for you, just and you will see it in the notes as well, and you can meditate on that a little bit more, is just hadronic production of TT-bar hadronic production. So TT-bar hadronic production has been a milestone calculation that is now known at next to leading order of QCD. So it's a two pattern calculations. Has been extremely sort of really cutting edge calculations for the past several years. It still is. It's the hardest probably of the 2-to-2 processes that we can calculate. That has required an incredible developments both from the analytical and theoretical point of view. But the results are again astonishing, right? So here is a comparison with data from the LHC and all the data from the Tevatron that was just down here. So this is the Tevatron. These are data from the LHC. And here in the blow up, you see the comparison of theory with data. And this comparison is meaningful only if you go to this order of precision. Otherwise, it will not tell you anything about theory. But this is something that tells you how accurate the level of theoretical predictions that we are gaining through that complicated matching of hard perturbative QCD prediction with the perturbative QCD evolution of pattern distribution functions and the perturbative QCD evolution of the shower processes that come after the production of a T and a T bar, how they all conspire, if you want, to provide an agreement with data that allows us to derive a value of the top mass so precise that we can use that value into precision tests of the standard model to constrain new physics. So again, in the plot on the right, you see the convergence of the perturbative expansion from the blue band that is LO to the pinkish orangish band that is the NLO to the NNLO band. The first two almost compatible, not quite. The second one fully compatible with the previous one. Again, a nice convergence of the perturbative series. Again, a message that had you worked with the leading order or even the next to leading order predictions, you would have not done a mistake, but clearly you would have had a margin of theoretical error, of a theoretical uncertainty that would have completely impaired the efficient and fruitful use of experimental results. And a similar example, an even more, not more meaningful, but different yet very striking example is, and I want to conclude with this, is the example of Higgs production. So Higgs production mainly happened via gluon-gluon fusion, and one of the main achievements of the last few years has been the prediction of this process that happens at the lowest order at one loop, as a matter of fact, because it's mediated by a loop of top quarks, how this process has been calculated in the past few years up to the third order of perturbative QCD. And the result for that calculation is evident. So the impact of that calculation is, first of all, crucial because of the fact that this is the main production mode and the discovery of the Higgs is based on this mode. But had we not had at least the second order of corrections to the perturbative prediction and the third order of correction to the perturbative prediction of this process, we would have not been able to compare theory to experiment at the level at which it has been done for the discovery of the Higgs. And probably the discovery itself of the Higgs would have not been such an easy achievement, probably not achievable even. And the reason for that is, again, in a plot that now is very similar to what you have seen before, in which you see the cross-section as a function of the center of mass energy and the width of the bands that are reproduced, that are given in the plot, illustrate for you the uncertainty that you have at each perturbative order. And it illustrate for you how the transition from leading order to next to leading order is not even represented by the naive uncertainty that you have on renormalization and factorization scale. It's really a completely different new step that you take in going from leading order to next to leading order. In this case, justified by the fact that the process all of a sudden becomes from a 2 to 1 to 2 to 2 process. And then it's only from that point on that you can really see the convergence of the perturbative expansion. And it's only by the third order that you really see the perturbative convergence down to a point that now the residual theoretical error is at the 5–6% level. And I've given here for you just for the sake of your inspection. We're not going to comment about these numbers, but if you have time to review these notes, I would just suggest that you read through the contributions of all the different steps, from the leading order to the next to leading order to the next to leading order in different approximation to the NQ below, and see how much each one added to the picture in order not only to increase and bring the central value to the correct value that would have been off by 100% or more if not for the higher order corrections, but also to reduce the uncertainty that given a central value you have on that central value, that is here also illustrated on the right-hand plot in a different way, just by plotting exactly, specifically the scale dependence, not illustrated just as a band. So the scale dependence on this plot is the band in the left-hand plot where the cross-section is plotted as a function of the square root of s. So I would, you will find all the discussion summarized in my notes, and I would probably add a little bit more information on these plots, like where they come, so that you can go and read the paper and figure out exactly all the little details if you're interested. And I'll be more than happy to discuss things with you either now or later. You know what to find me.
Right, thank you. There's one question. If the perturbation at NLO is not stable or not converging, how do you determine to which order we should go?
Well, the first thing, you need to understand why, right? So the fact that leading order and next to leading order look so different one from the other, and therefore your it seems like one order of QCD corrections completely upsets your lowest order prediction, has to have a reason, right? Now, corrections, NLO corrections, as you have seen here, of course, I have illustrated for you examples in which they were large. That's not always the case. That can also be small, depending on the process. You need to understand why. So if you see, like in the case of that we illustrated first, so in the Trillium case, you see a large effect. You know why? It's the extra channel that comes in. And that may depend on the energy. You look at that at the tevatron, you see less. You look at that at the LHC, you see much more, just because the gluon density is larger. So you need to understand why. It's also the moving from a 2-2 to a 2-1 to a 2-2 dynamics. So you bring in, as in the case of the Higgs, a totally different kinematics. A totally different kinematics may bring in a different emphasis on, for instance, soft and collinear regions of the process. So the reality of things, the production of a Z or the production of a Higgs in a hadron-hadron collision has all that dynamics in it. We are the people who are trying to kind of get access to it, to that description a little bit at a time. So it's our problem if we are approximate in building the full picture. So as soon as we move the next step, all of a sudden we bring in such a much richer kinematics that is due to the fact that we go from a 2-1 to a 2-2. We know that QCD has some emphasis on soft and collinear regions, so we need to take that into account. We need to inspect how that influences the cross-section. So that may give some intuition of why the cross-section has changed that much. There may be more, like in the case of the Higgs, you add QCD in the final state, you are changing the color structure of the process itself. Here we are producing a color singlet. When you add an extra gluon to the process, you're changing the color structure of the process. QCD may affect the cross-section in going from the lowest order to the next, also this way, because you wouldn't have seen it in a theory without the non-abelian gauge structure, but you see it in QCD. So there may be many reasons. So you have to understand why that difference is there. It may also be that you need to explore the behavior of your cross-section over a range. So what I mean is just that often you may have seen situations in which the leading order cross-section has a dependence on the scale that is very sharp, like that. And this is basically the running of alpha S. That's typically what is induced. A leading order cross-section, mu dependence is typically the dependence induced by the dependence of alpha S on the scale, on the renormalization scale. And then if you distinguish between renormalization and factorization scale, there may be some nuisance attached to that. And so this is your LO. The NLO many times has a behavior like this already. For some processes, it's not the case. As we have seen, you have to go to much higher order to get that. But let's see, it's a good process. So it's a process that at NLO already reaches a large range of scales over which it has a plateau. And this is the ideal situation in which you would say, oh, I'm done. So I don't have to calculate any other order because I already see that the dependence on the scale is basically flat at NLO. Right? Now, you may see these, now I've exaggerated in building such an incredibly nice plateau for such a long, such a wide range of scale. But if you were so, if you had to look at this very same process and the cross-section, the leading order cross-section and analog cross-section, down here, you would see a difference. If you had to look at that down here, you would see a big difference. This is it's a sort of crazy example. Nobody would do that. But the message here is just that the difference between a law and an law depends, or if you had to look at the difference between the two, is very much scale dependent. So if you look at a process, you really have to investigate the process thoroughly in order to understand where the difference between a law and an law comes from and why. So if you see a situation in which the NLO does not stabilize, you need to add another order. If you see a situation in which the difference between a law and an law is huge and is not compensated is not, if you want, accounted for by the expected scale dependence of the LO and the NLO, you have to add one order. And within, as we said, if you want, as we have seen in the examples we have looked at, within a couple of orders at most, you would see, since not many things can keep happening, openings of new channels, adding new kinematic features or anything else, you would expect within the first 2-3 orders things to very much show this kind of behavior. I don't have an example in mind in which this doesn't happen. So it's very much a game of understanding why the difference, the behavior that you see is what it is. And the things that you want to explore are a handful of things that are very often dictated by understanding the physics of the process itself, like the scale that you want to choose. It depends what you may see that certain processes stabilizes around a scale that is different from what you expected to start with, but then you need to understand why. And there is typically a reason, that is a physics reason for that.
Okay, thank you. I think we should probably wrap up at this point. Let's thank Laura very much for these enlightening and really interesting lectures, and talk to you later.
Okay, thank you. Bye, everybody.